Hi, welcome along. Quick little video on force oscillations and resonance. Should be quite dramatic, some of this. Good bit of physics. We're going to have a look at a couple of clips of resonance in action. This is the very famous Tacoma Narrows video. It's a suspension bridge built in America, and there's about a 35-mile-an-hour wind blowing across. It's not a huge wind. You can see it's resulting in this very definitely oscillating behaviour on the bridge. Very brave bald man there. Always best to acknowledge the bald community. And you'll see that eventually this becomes quite catastrophic. I think the bald man was trying to rescue the dog in the car, apparently. You can see there the bridge, very expensive thing. No one hurt, but massive destruction. The other famous kind of example, and what we see here is somebody trying to break a glass by singing, going "Ooh!" and the glass. What the straw is doing is showing him whether he's on the right frequency. Bang! There you go. He's managed to break the glass by singing, and he's now going yeah, 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 which is my kind of best rock star yeah. Okay, in slow mo. So what we're doing here is just a little practical simulation. Just going to look at this whole business of forced oscillations and some of the behaviours. So what we've been looking at, previously in the rest of the topic was what's called free oscillations. We pull a pendulum to the side and let it go, and it vibrates from side to side, or we grab a spring and we pull it, put a mass on it and pull it down, and it starts to oscillate. Here we've got a mass on a spring, but it's being driven by that platform going up and down, and the technical term for that is it's being driven by a periodic driving force. Currently we're driving it at a frequency of 0.5 hertz, and you're probably thinking, John, we've seen some pretty dull things in this video, but this may be the most dull so far. Well, I don't know whether it's going to get exciting, but we're certainly going to see some change. What you need to notice is that we're getting very little movement of the mass. The spring is effectively working as a rigid bar, and they're moving in phase. And we'll come back and we'll recap again this in a moment. I'm just going to change it now to 2 hertz. Obviously, I've kind of rehearsed a little bit of a sequence here. It's going to take a little while to settle down. The mass isn't really moving that much. Moving a bit. Actually, I might go to a higher frequency, even higher. It's just taking, I'm just out of sight here, I'm just going to add a little bit of damping, just take away a bit of energy. Ah, that's better. We'll come back to 2 hertz again. I think that motion was in part left from before. Now the platform and the mass are out of phase with each other, aren't they? You can just about see the grey thing going up and the mass coming down. But again, not wildly exciting. But look what happens if we set it. Well, actually, no, let's just turn the platform off. Use some damping to get rid of the motion. And I'm just going to make it back into a free oscillator. And you can see, take my word for it, that's now oscillating at about 1 hertz. That's the frequency it wants to vibrate. I'm just going to bring it to a stop. Now let's see what happens if the platform works at the frequency this wants to vibrate at. You can see we're starting to build up more motion. No, I haven't pressed enter yet. That's why it's not working. Now we're building up more motion. The phase relationship here is more complicated. I think we'll have to look in another app for that. But you can see there we're really building up this big catastrophic oscillation. So this is resonance that you're observing. It's where the driving frequency of a force oscillation is equal to the natural frequency, and that's what we've seen causing the destruction in the previous videos. Adding a little bit more now. Got a whole bunch of masses on springs, and you can see like number 9 is on a stiff spring, and it's got a small mass. It wants to vibrate at a larger frequency, 5 hertz. This one still wants to vibrate at 1 hertz, and we've kind of rigged it so that the middle one wants to vibrate at 1 hertz. Bung in a bit of damping just so they're all starting nice and still. Number 5 wants to vibrate at 3 hertz, which is what the platform's going to vibrate at. So let's turn it on and see what happens. So on the left here, where we've got number 1, what we said before was then we're now driving this oscillator at a frequency much, much higher than it wants to vibrate at. So we get very little movement of the oscillator, and the platform and the oscillator are out of phase. However, the system is moving at 3 hertz. Everything here is moving up and down at 3 hertz. Number 5 is resonating, isn't it? Because it's the periodic driving force matches its natural frequency, causing this catastrophic behavior. I'm going to slow the simulation right down. And if we just watch, you can see platform gets the top, mass gets the top. Platform gets the top, mass gets the bottom. Platform gets the bottom, mass gets the bottom. So the platform leads the driver by about 1/4 of a cycle, or pi/2 radians. And number 9, here we're inputting energy at a frequency much lower than the natural frequency. So the spring is acting as a rigid bar. So 9's amplitude is basically the same as the amplitude of the platform. The number 9 is in phase with the platform. So we have 0 radians phase difference. So let's just go back. Number 5, large catastrophic oscillations. Driver leads oscillator by pi/2 radians. And then number 1, the driver and the oscillator are out of phase by pi radians, and the amplitude is very small. It's actually smaller than that of the platform. I think we'll leave it there for that video to get you some very basic questions, and then we'll come back and summarize all this in a nice diagram and talk a bit more about what we mean by damping.